0 and 1. They are fundamental building blocks of modern computing. But is that all? Today, let's give us a taste of quantum computing. Hello everyone, this is Jay from BTYT Tech Library. Semiconductors are undergone significant advancement since their adoption in systems based on the von Neumann architecture, where they play a crucial role as key components. As their application expanded, semiconductors were categorized into two primary types: logic circuit and memory devices. Logic circuits are responsible for executing operations and controlling the flow of information by manipulating binary data, zeros and ones, using switches that represent Boolean algebraic functions. Digital logic is the application of the Boolean algebra of 0 and 1 to electronic hardware consisting of logic gates connected to form a circuit diagram. Each gate implements a Boolean operation and is depicted schematically by a shape indicating the operation. Obviously, with more switches, you can do more complex calculations. The need for more efficient systems, characterized by increased integration, reduced product volume, and lower power consumption, drove the creation of semiconductor integrated circuit technology, specifically CMOS technology. As a result, computers today rely on this technology to implement the von Neumann architecture, which forms the foundation of modern computing systems. What if not only 0-1? In traditional computing, information is conveyed through bytes, which are concise messages consisting of an 8-bit code that can only be represented by two values, 0 or 1. However, in the realm of quantum mechanics, particles can exist in a state of superposition, where they can represent both binary states simultaneously, allowing for the creation of quantum bits or qubits. By leveraging entangled qubits, quantum computers can process an exponentially larger numbers of possibilities in parallel, enabling algorithms to tackle complex tasks that are currently unsolvable or impractically slow. In contrast, even the most powerful modern computers would struggle to solve these problems with a reasonable time frame, often requiring years if not decades, whereas a quantum computer could perform the same calculation in mere seconds. Alright then, how can we express this? We can use vector notation. The probability of measuring psi as 0 is the absolute value of alpha squared. The probability of measuring psi as 1 is the absolute value of beta squared. That means before measuring the qubit in part 0, part 1 state, we don't have definite result, but when we measure it collapsing into the 0 or 1 state, we can factor out alpha and beta. On the right hand side of the equation, the column vector represents 0 and 1 states. With Dirac notation, alpha gets 0 plus beta gets 1. To visualize qubit, we can use Bloch sphere. The Bloch sphere is a geometric representation used in quantum mechanics to visualize the state of a qubit, which is the fundamental unit of quantum information. It provides a way to map all possible states of a single qubit onto the surface of a unit sphere, making it easier to understand and manipulate these states. Like classical bit operations, quantum bit also has several operations. Let's take a look at some of them. CNOT operation, also called X-gate, implements a rotational pi around the x-axis of the Bloch sphere. Hadamard operation puts a qubit into a state of equal superposition. It implements a rotational pi over 2 around the y-axis of the Bloch sphere. Z-gate, phase flip operation, rotation around the z-axis of the Bloch sphere by pi radians. And identity operation, it leaves the basis states unchanged. Okay, now working on multi-qubit, expressing in 2 qubit in Dirac notation. with vector notation. About the 2-qubit operation, we need to check another fundamental quantum logic gate, CNOT Gate. It operates on 2 qubits, a control qubit and a target qubit. If the control qubit is in the state of 1, the CNOT gates flip the state of the target qubit from 0 to 1, or vice versa. If the control qubit is in the state 0, the target qubit remains unchanged. Good. With this, now let's have a look at a very interesting quantum algorithm. Deutsch's algorithm is a quantum algorithm designed to determine whether a given Boolean function is constant or balanced. The function takes a single bit as an input and returns a single bit as output. A constant function always returns the same output, regardless of the input, while a balanced function returns 0 for one input and 1 for the other. On a classical computer, we need to query twice, to compare the result of f of 0 and f of 1 to see if they are the same or different. How does a quantum computer help with this problem, and what does it tell us? In a perfectly quantum system, the law of conservation of energy imposes a fundamental constraint. Any process must be reversible. This requirement stems from the mathematical underpinning of quantum mechanics, where reversibility is ensured by the property of unitary operations. Actually, we can rewrite this function with addition modulo 2, which is a reversible operation. So, we can make the following quantum circuits for 4 options. Initially, we have the state, psi 0. Through the Hadamard gates put in the superposition state, psi 1. On the quantum oracle, we have 4 scenarios, which factorized as psi 2. And use the Hadamard gate on the first qubit again, we get psi 3. As a final step, when we measure the first qubit, it always shows 0 if the function is constant, and 1 if the function is balanced. Voila! With a quantum computer, we can figure out if the function is constant or balanced by only querying one time. Deutsch's algorithm inspired many quantum algorithms like Deutsch-Jozsa algorithm and Shor's algorithm, and shows potential for exponential speedup over classical computing. What other interesting things are there about quantum computers? In quantum computing, traditional loops and conditional statements as seen in classical programming languages are not directly implemented within quantum circuits. In the foreseeable future, it's hard to see quantum computing rule over all the other computing. Just as GPUs and NPUs work with CPUs in graphic processing and tensor calculations, quantum computers are more likely to cooperate with classical computers because of their characteristics. Today, we started from the differences between classical computing and quantum computing and briefly discussed quantum supremacy by constructing a quantum circuit. If there is a chance, I would like to occasionally cover quantum computing as well. Oh, and I heard that this year is the International Year of Quantum Science and Technology. Happy 100th anniversary, quantum mechanics!